To understand the forces at play in heavy infrastructure, look at the sheer mass resting on the Earth. Thousands of tons of steel and concrete are ultimately supported by foundation columns hidden deep underground. The structural integrity of this building relies on theoretical calculations. Engineers determine how much downward load these subterranean piles can safely absorb by calculating the friction along the sides of the shaft and the bearing resistance at the very tip. Engineering equations assume a level of uniformity that nature rarely provides. Underground soil strata are chaotic, unpredictable mixtures of sand, clay, and rock that react differently under massive stress. This uncertainty necessitates the initial vertical compression pile load test. It is a physical operation designed to simulate the maximum anticipated stress of the final superstructure before construction begins. To guarantee safety, engineers must force the earth to physically bear the load and prove the math before a single brick is laid. We can examine this process through the methodology report for the Wagon Examination Depot in Badapur, where engineers are preparing to test a reinforced concrete board cast in situ foundation pile. The physical dimensions of the test subject are specific. It is a single pile measuring 600 millimeters in diameter. The column must prove it can handle a safe vertical working load of 75.1 tons, as specified in the structural design philosophy. This procedure is governed by strict parameters outlined by the Bureau of Indian Standards in IS 2911 and executed by an accredited testing agency carrying a specific NABL certificate to ensure precise instrument calibration. This methodology report functions as the legally binding blueprint for translating microscopic soil movement into a valid structural safety certification. The setup begins by addressing the raw contact point. The uneven pile head is chipped down to expose dense, uncompromised concrete for reliable load transfer. To prevent concrete from crushing unevenly, the pile head is leveled and capped with epoxy grout. A thick steel bearing plate is seated flush against it. The mechanism delivering the compressive load is a 250-ton capacity hydraulic jack, positioned squarely in the plate's center. As the hydraulic pump forces fluid into the system, the resulting pressure readings on the gauge are converted into a physical ton value using the jack's specific ram area correction factor. When the hydraulic pump activates, the ram of the jack extends and pushes upward, moving away from the pile head. To drive the pile downward into the earth, this upward force requires an equal and immovable reaction point positioned directly above it. That reaction point is the Kentledge arrangement. Primary and secondary steel girders are assembled directly over the jack to construct a rigid, massive reaction frame. This platform is loaded with dead weight, concrete blocks or steel billets, creating the downward counterforce necessary to redirect the jack's energy back into the foundation. The arrangement of this weight requires strict geometric symmetry. The cumulative center of gravity of the stacked concrete must align with the central vertical axis of the pile beneath it. If the weight distribution is off by even a slight margin, the upward pressure of the jack will create eccentric moments, a twisting force that can trigger a structural failure of the entire rig under peak pressure. A successful test relies on the structural symmetry of this reaction frame to safely harness the strength of the hydraulic system. The methodology report for this site contains a numerical discrepancy. One section specifies a maximum test load of 187.75 tons, while the section governing the physical reaction setup limits the design to a peak load of 112.65 tons. This highlights the standard safety factors applied to testing equipment. To guarantee stability, the dead weight stacked on the platform must be 1.25 times the maximum intended test load. To safely push 112.65 tons into the earth, the reaction frame above it must carry exactly 140.81 tons of dead weight to ensure it does not yield. Regardless of the documentation error, the physical test is limited by the mathematical capacity of the Kentledge present on site. The rig is physically capped at this 140.81 ton safety limit. Measuring these massive forces requires instrumentation capable of tracking movement at a sub-millimeter scale. Engineers deploy 4 independent mechanical dial gauges to track the pile's settlement. These instruments have a sensitive least count of 0.01 millimeters. This high precision creates an isolation problem. As the foundation pile yields under pressure, it drags the immediate surrounding soil downward. If instruments rest on sinking soil, data is corrupted as the reference point moves. To solve this, engineers install datum bars. These beams cross the pile, but anchor far outside the soil depression, at least 3 times the pile's diameter away. The 4 dial gauges are affixed to these isolated datum bars. Their measurement spindles rest on smooth glass plates glued to the pile head, allowing them to capture only the true vertical movement of the concrete. Capturing accurate data requires mechanically isolating the sensitive measuring tools from the destructive forces of the test itself. Once the system is calibrated and isolated, force is applied in controlled increments of 20% of the working load. At each stage, engineers wait. They cannot advance the jack to the next load tier until the downward settlement rate of the pile slows to less than 0.2 millimeters per hour. The process peaks when the rig achieves the maximum test load. At this threshold, the hydraulic system is locked down to sustain that pressure for a continuous 24-hour hold. This is an active process. The hydraulic pump operator must monitor the manifold and pump fluid back into the system to counteract pressure drops as the soil yields over a full day and night. This 24-hour hold proves the foundation can sustain structural loads without yielding, validating its long-term stability in the specific soil strata of the site. Following the hold, the pile is slowly unloaded. As the weight is removed, the instruments record the elastic rebound, the amount the pile naturally springs back upward as the soil recovers. This data is plotted to create the load versus settlement curve. This chart maps the complete behavioral profile of the foundation, showing the exact relationship between the applied force and the resulting movement. This data curve is measured against the legally binding acceptance criteria established in IS 2911 to determine structural success. For this project, the threshold is absolute. At the safe working load of 75.1 tons, the total settlement of the column cannot exceed 18.00 millimeters. Through this combination of massive mechanical leverage and micrometer-level precision, theoretical design is finally forged into empirically proven, safe infrastructure.